And if we go over the first quiz, well, the second quiz is about theory concepts and about units. But first, we have this one, okay? And it's always the same. So it's we are going to use these concepts now because we are talking, or we will start talking as of next week about solar heat gains and the PV panels or solar heat collectors, and we need to know we need to understand that we are receiving a huge amount of energy from the sun, and then we can turn this energy into electricity if we are using PV panels, or we can turn that energy into heat if we are using solar collectors. So we can heat up water, and that's fine because in our heating systems, we need hot water, or in our domestic hot water systems, when we are having a shower, or we are taking a shower or whatever, we need hot water. So hot water is something useful in buildings. But electricity is even more useful. By using these two kind of solar devices, we can use either solar thermal collectors or PV panels, photovoltaic panels. We can turn that heat, that energy from the sun into heat or electricity. And this is what we are going to do in this second part of this course. We are going to work with these solar devices, which are considered renewable energy. So we are going to integrate renewable energy devices in our buildings. And we need to understand that we are receiving this from the sun, and what we receive from the sun is the solar irradiance. Okay, so this is the concept, and it's measured in watts per square meter. So this is a unit of area, and this is a unit of power. Okay, so when we are working with watts, this is power, and square meters or square feet or whatever is the area, or the area of the surface. In this case, we're talking about a window. We can talk about a window, a roof, or a PV panel. So if we know the area of that element, and we know the solar irradiance, we know the energy that is received in a specific time. In this case, is 1 hour. Okay, so probably we have to, if we want to talk about energy, we can have irradiance, we can have area, and finally time. The irradiance is the energy that we receive from the sun, but we don't talk about energy. We talk about this irradiance because it's power divided by square feet, and then we have to turn that into energy. Okay, so let's do it as an example. So the first one is the area is 10 square meters, the solar irradiance is 200, and the energy received, we have to calculate the energy received in 1 hour, okay? So the irradiance is 200 watts per square meter. Let's make it bigger. And let's make that smaller. Times the area. The area is 10 square meters. Okay, 10 square meters times the time, and time is 1 hour. Okay, so we calculate this, and this is 2,000 units. We can cancel square meters. And square meters. Okay, so this is watts times hour. So the units here are watts hour. But these units have to be in kilowatts. So if we want to convert watts into kilowatts, we have to divide by 1,000. So that would be 2,000, no, 2, sorry, kilowatt hour. So the right answer here is 2. Okay. We can do this with an Excel file. We can have the area. So if we do this with the Excel file, we call this Irradiance. We have 200. The area is 10, and the time is 1. Okay. And if we're working with watts per square meter, the area would be square meters time. Thank God the time is always hours. Hour. So what is the energy? The energy equals this times this times this. But these units are watts hour, because this is watts, square meter, and hour. Okay, so this is watts per hour. If we want to turn this into kilowatt hours, we have to divide this by 1,000. So 2. Okay. We can do the same with different units. We can do the same with imperial units. So in imperial units, what is the unit of, what's the unit for energy? I don't think we need this column. The unit for energy in imperial units is BTU. The irradiance will come in BTU hour, and square feet. The area is in square feet, and time is in hours. Okay, so if we multiply this, we will end up having BTUs. We will do that in another question, but it's always the same. The other way around, if we have power, or we want to get the power and we have the energy, then we have to divide the energy by the time, and then we will end up having the power. And it's always the same formula, but we need to know that energy, well, we need to be aware of units. We use kilowatt hours. If you look at your electricity bill, you pay for kilowatt hours. So you better get used to this unit, because this is what you are paying for. If you are looking at your gas bill, probably you will be paying for therms. And therms, I think it's 100,000 BTUs, but we pay for energy. So we have a power in our boiler, we have a power in our device, and then it depends on how many hours we are using that device, then we pay for the energy. Okay, so if we have a powerful boiler, but we don't use it, we pay 0. Well, we don't pay 0 because we always have to pay taxes, and so we never pay 0. But if you are using a powerful machine 24 hours a day, then you pay a lot, because you are using a powerful machine 24 hours a day. If you reduce the power and you use it 24 hours a day, you pay less. And if you reduce the power and then you are not using that 24 hours, but you are using only the operating hours of the building, can be 8, 10, 12 hours, then you pay even less. Okay, so I think by talking about money, everybody understands. Talking about energy and watts and kilowatts and hours and whatever, it's difficult. But if we talk about dollars, you will understand it easily. Okay, so the first question is what is the, okay, so here we have the solar irradiance. These are different units. This is the area, 100 square feet. This is the solar irradiance, and we have 2 hours. Okay, so if we go back here, the irradiance is 200 BTU hour feet square. The area is 100 square feet. Time is 2 hours. So this energy in BTUs is 40,000. Okay, question 3. The daily energy, so here we have the energy received on a solar PV panel is 10,000 BTUs. Okay, so here, if we want to calculate the power, the energy that we receive is 10,000, let's make it bigger. Is 10,000 units BTU. If the surface area of the panel is 10 and there are 10 hours of sun, so here the sun is 10 hours. And we have the area. Okay, so power, let's call this irradiance, is energy divided by times the time times area. So the time is 10 hours. The area is 10 square feet. Vale. 10 square feet. So what is the irradiance? The irradiance will be the energy divided by the time. Well, we can have a bracket here, times the area. There you go. So the irradiance is 100. We have the energy in BTUs, and the final units are BTU divided by hour divided by feet square. Okay, so this is BTU divided by hour divided by feet square. So it's 100. Question 4. A vertical window with a surface area receives the solar radiance. What is the energy? Okay, so here we have to calculate energy again. And we are using kilowatt hours. So the window, the irradiance is 100. The surface area is 20. And time is 1 hour. So here the energy is 2,000, but we have to give this in kilowatt hours, so it's 2. Question 5, the solar irradiance, this is in BTUs, so the irradiance is 1,000. No, sorry, the irradiance is 200. The area is 1,000. The square feet, and the time is 10 hours. So we are having 2 million BTUs. Question 6, the daily energy received on a roof is this. So here we have the daily energy received on this roof. It's 100,000. So this is 100,000. The surface area of the roof is 100. And there are 10 hours of sun. So we are receiving 100. The irradiance in BTU hour feet square is 100. Question 7. Now the solar irradiance, it's we're talking about international units again. So it's 200 watts per square meter. The roof, the area is 100. And time, 2 hours. This is in watt hours, but we have to give the answer in kilowatt hours. So this is 40. The vertical window receives a solar irradiance of 100 BTU hour. So we have to go to this one. We receive 100. The area is 20. And the time is 1. So this is 2000 BTU. Question 9, the daily energy received on a roof. So here we have to work with this. We are receiving 10 kilowatt hours. Okay, so I think we can open another. Yep. So let's talk about kilowatt hours. And here we need to talk about square meters. So we are receiving 10 kilowatt hours, 10. The surface area, the area is 100 here. And there are 10 hours. So have 10 hours of sun. What is the average irradiance in watts per square meter? Okay, so that's interesting because here we are talking about kilowatts. So if we want to turn this into watts, we can copy this here. Because if we are talking about watts, that equals kilowatts times 1,000. And vaya. Okay, so that would be watts hour. If this is kilowatt hour, if we want to turn this into watt hour, it has to be multiplied by 1,000. And now, yeah, we have to change this. There you go. Okay, so this is the energy in watt hours divided by square meters. So the irradiance, this irradiance is in watt per square meter. So this is 10. And finally, the solar irradiance on a, okay, so here we have to work with this. The irradiance is 200. I have 1 minute left. 200, the solar, the area is 100. And the time is 1 hour. So that would be 2000, 20,000. Submit. Okay, correct. Great. Okay, the time is tight, I know. But if you have, I know if you know what to do, it takes a couple of minutes. and it's always the same. It's about the concept, the difference between energy and power, or the difference between irradiance and energy. And then we have to be careful with units. And units are the most important thing here, because if you mistake units, if you say, okay, I'm using 40,000 kilowatt hours. No, you are using 40,000 watt hour because you are paying for that. So if you tell your client, if you mistake watt hours for kilowatt hours, your client will end up paying 1,000 times more. Okay, so that's why units are important. Or the units between, or the difference between kilowatt hours and BTUs. So here it's 40, here it's 20,000. Okay, so be careful with that because units mean money. When you turn units into dollars, you have to make sure that you have the right unit, because otherwise you can either multiply by 1,000 or divide by 1,000. But anyway, it would be a huge mistake. Okay, so be careful with these units. And then the second quiz was about basic concepts we can preview. So here there are no formulas. It's about understanding the concepts, and we are using these concepts in all these building science and building systems courses. We are using the same concepts: the thermal resistance, the U factor, the U value, or the thermal transmittance, or the solar heat gain coefficient. Okay, so we have to become familiar with this because again, that matters. So what is the thermal resistance? Is the ability to retard heat flow? Yeah, it sounds well. Is the U factor? No, the U factor is the inverse of the thermal resistance. Is the amount of heat that flows through the wall? This is not the thermal resistance. Is the plaster applied? So it doesn't make any sense. So it's the ability to retard heat flow. Thermal resistance, the ability to retard heat flow. So that makes sense. The thermal transmittance. Okay, what is the thermal transmittance? Is the heat flow through a layered building component like a wall? I think this is the right option. Is a vertical element used to build a wall? No. Express the ability to retard heat flow? No, this is the thermal resistance. The thermal resistance expresses the ability to retard heat flow, but the thermal transmittance is the heat flow through a building component. Is the R value? No, the R value is the thermal resistance. So I think this is the first one. Question 3. The solar heat gain coefficient is, we will go this way. So the visible light of solar radiation, no. Is the ability of a material to store heat? No, it doesn't have anything to do with this. Is the ratio of solar heat gain through a window to incident solar heat? This is the concept of solar heat gain. Okay, so the solar heat gain, if we have a window, if there's a wall here with a window, okay, and here we have the sun, the sunlight. Let's turn it to yellow. Okay, here we have a protection. So there's a window here, there's a glass, so we can have a glass here. So this glass has a solar heat gain coefficient. You can insert text. Okay, so here we have a solar heat gain coefficient on this glass. And So that solar heat gain coefficient can do different things. We can reflect part of that energy. Okay, so part of that energy will be reflected. Part of the energy will be absorbed in the glass. Okay, so the glass heats up. So that means that it's absorbing some energy, and part of the energy will be transmitted inside. Okay. So if this is what we receive from the sun is the irradiance. Okay, so we can have a percentage of reflected energy. We can have a percentage of absorbed energy. And finally, we have a percentage of transmitted energy. Okay, so the solar heat gain coefficient, the solar heat gain coefficient is the ratio between the transmitted energy and the total irradiance that comes from the sun. Okay, so that's why the solar heat gain coefficient is always between 0 and 1. So imagine that we have 100% of transmittance, then the solar heat gain coefficient would be 1. So if nothing is reflected and nothing is absorbed, everything is transmitted. So the solar heat gain coefficient is 1. If we had an opaque wall, so if it's not transparent at all, nothing is transmitted. So everything will be, the solar heat gain coefficient would be 0. Okay. The higher the solar heat gain coefficient, so the closer to 1, the more transparent the glass is. And the less the solar heat gain coefficient, or the lower the solar heat gain coefficient, the less transparent the glass is. Okay, so that's the concept of solar heat gain coefficient. It's a ratio of solar heat gain through the window to incident solar heat. Okay, so the transmitted divided by the total irradiance. What are the units of R value? Well, this is basic. You need to know the units. We have these units with feet square, Fahrenheit, hour divided by BTU. But the units of the thermal transmittance is inverse. So it's BTU divided by hour, feet square, and Fahrenheit. Okay, so you don't have to think about this. So if you see this, okay, this is thermal resistance. If you see these units, this is thermal transmittance. So you have to internalize these units. The units of energy. Okay, so here we have the same question. Is this a unit of energy? No, this is the unit for the thermal transmittance. This is not energy. Is kilowatt hours in imperial units and BTU in international units? BTU is imperial and kilowatt hours is international. So there's a mistake here. Is BTU in imperial and kilowatt hours in international? Yes, this is the right answer. Because BTU hour or kilowatt, this is for power, it's not for energy. And now we have the units of power. Is it BTU in imperial and kilowatt hour international? No, this is energy. Kilowatt hour is energy. So BTU hour is the unit of power in imperial units. So this is the right answer. The wet bulb temperature. So you remember what the wet bulb temperature was? Wet bulb temperature. Okay, the wet bulb temperature is the temperature of a thermometer that is wet, or is soaked, or is completely, it's not under the water, but is completely covered with moisture. Okay, so it's not under the water, but it's completely wet. So that's the concept of this wet bulb temperature. Yeah, so this is easier to understand. So imagine that we have a piece of cloth that is wet around the bulb, this thermometer. So that will be measuring the wet bulb temperature. And usually, if we have the same conditions, if we have a dry bulb temperature, it's always higher than the wet bulb. Okay. So what is the question here? The wet bulb temperature is the internal heat measured in, no, the temperature of a dampened thermometer. Yes, so this is the air temperature measured by, no, is the temperature of a damp, wet thermometer. The sensible heat is the ratio of solar heat gain through a window to incident. The sensible heat, okay, so that's, you know that we have sensible and latent heat. Okay. So the sensible heat, well, this is too complicated. Basically, the sensible heat, it has to do with temperature. So when we change the temperature, we change the sensible heat. But latent heat is the heat that we gain without changing the temperature. So it has to do with moisture. When we have moisture in the air, we can increase the amount of energy of that air without changing the temperature, because we are, this heat or this energy is gained by the moisture. Okay, so that's why we call this latent. Latent, it's a word that comes from Latin. Okay, so it's secret, unknown. This is what latent or latente means in Latin. So it's something that we don't know or we don't feel. We can feel that the temperature is changing. So this is sensible, but we can feel it. But latent is something that we cannot see or we cannot even feel, because it's within the moisture. And yes, so the moisture is absorbing heat, it's absorbing energy, but human beings don't feel this. Okay, so that's the difference between the sensible and and the latent. So the sensible heat is the heat absorbed by a material which raises the temperature. So that's the, so sensible has to do with temperature. Okay. What is the thermal envelope of a building? I think Peter Joost was talking about this thermal envelope, and he explained it within in a graphical way. So you can, the thermal envelope of the building is the line that you can trace without moving your pen from the paper. So you don't have to interrupt the thermal insulation. So this is the thermal envelope of a building. So it's a line or plane where insulation and air barrier exist in order to resist the thermal transmission. Okay, so this is the definition. None of the others are correct. Okay, so it's the line where you place the thermal insulation, air barriers through the building shell. Okay, so this is the thermal envelope. And we are done, I think. Yep. Submit quiz. And correct. Yep. Great. Okay, so I'll keep posting these kind of quizzes with basic knowledge because I think there's nothing new here, but you have to remember those basic concepts. And not only you have to remember these basic concepts for this course, but for your professional development, you need to remember this. You don't have to make, for sure, we always have questions sometimes, and sometimes I forget, and BTU, was it energy? Okay, but this existential doubt should last only for a few seconds. Immediately you said, okay, BTUs, energy in imperial units, kilowatt hours. So you have to internalize this, because your client will end up paying for the energy that your building, or the building that you have designed, is using or is wasting. So make sure that you understand these concepts. There are a lot of things, there are a lot of concepts. We have thermal resistance, thermal transmittance, we have the energy, the power, irradiance, imperial units, international units. It's tough, but you have to master these concepts and these units. Okay, so before moving on with Revit, I posted an announcement that here in Revit 2021, they have it's not a plugin, it's an add-on. They call it an add-on, solar analysis for Revit 2021. So it's not in Insight, because Revit 2021 has a different way. So it has Insight embedded, so you don't have to install a plugin. But they forgot, I think they forgot to work with this solar analysis. Okay, so if you click here, you find this website with all the product updates, and you have to search for solar. Here you go. So this is the solar analysis for Revit 2021. So you can click here, and it's quite, it's nothing, it's not heavy at all. And you have to download it, and then you have to click on that link or on that file, and it's installed immediately. Okay, so if you're using Revit 2021 on your laptop, make sure that you can come here. I don't think you have to even to use your account. I think this is for free. I think they realized that they made a mistake with this, and you can download it for free. Anyway, if you have to register, you can use your Kinestate email. And we have the lighting analysis for Revit 2021. This is also interesting. We're not using this in this course. We're not analyzing day lighting or natural light. We could do that, but we don't have time. Okay? But that's another interesting feature for Revit. So if you're working with the 2020, you can use the Insight. But if you're working with the 2021, use this one. I have tried so I have uploaded here on my computer. And the 2021 version, and it works. So I'm going to 370, 360. Okay, I'm using this one. It was created in 2020, and now I'm updating to 2021. Okay, so if we have this element, and if you click Analyze, you have this tab here, the solar, and it works the same way. You can go to Custom. You can go to select your surfaces. Okay, you select this, then you finish, and then you update, and it has the same analysis that we saw with the 2020. Okay, so it works exactly the same way. So we're going to use this in the second part of the course, but make sure that either if you're working with 2020 or 2021, you have this on your computer. If you're working with a computer lab desktops, I think I will be able to go back on campus, to be back on campus next week, and I'll make sure that all the computers there, they have this option, because probably, I don't know if you can install this option on the computers without permission. Okay, if you can't, I'll do it next week. And I think for the second part of the course, we can all work with this option, which is quite useful. But again, can we rely on Revit for this solar analysis? We need two different sources, and this is what we are going to do. We did this with the thermal loads. We use the Excel file, and we use the Revit loads report. And then by comparing these two options, we can understand, okay, we are doing well, or there's something wrong in one of the models. We will do the same thing with this option for the solar analysis. And we are going to use three different programs, or three different software, Revit, and two more free softwares that we can find on the internet. But again, we are comparing different sources. So if at the end, the results, at the end of this process, the results are the same, we can trust our calculations. If we have different results from different tools, that means that we have made a mistake somewhere. We don't know where, but there's a mistake if the results are not the same. Okay, so if you're working with Revit 2021, your computer, try to do this, try to install this plugin, and in Analyze, you will be able to find the solar analysis. But we are not going to work with this now. We're going to work with something easier. So today we're going to talk about ventilation. So this is the title of the lesson. Ventilation and infiltration. This is it. Okay, so those are two concepts that usually we we don't understand. No, it's not that we don't understand, but they are two similar concepts, and we can use infiltration for ventilation, or we can consider that we are ventilating the building because we do have infiltration. But nowadays it cannot happen. So we have to ventilate our building, and we have to prevent infiltration from happening. Okay, so that's the concept. So infiltration is the amount of outdoor air that enters the building, but it's not controlled, and it is unwanted. So we don't want this. Okay, so if we open a window, this is not infiltration, because we understand that we are opening a window and we control this opening. Infiltration happens between cracks of the building, or between joints, between the connection between the roof and the floor, or between the connection between the window frame and the wall. If it's not well sealed, if the construction is not quite good, we can have these infiltration issues. There are other factors that make this issue even more serious, which is the speed of air. If the wind is blowing too fast, then we can increase these infiltration issues. Infiltration always happens. I mean, it's impossible having zero infiltration, but we have to reduce it, because this is something that we can't control. Ventilation is the outdoor air that enters the building, the fresh air that enters the building, but we control that air. We can open a window for 10 minutes. Well, at least we can control when the window is open or when the window is closed. The better way to control, or the best way to control ventilation is using a mechanical ventilation. With a mechanical ventilation system, we control the rate, the ventilation rate, we control the CFM, we control the speed, we control the velocity of the air. This is, that happens in a mechanical system. That just by opening windows, we can control the amount of air that is entering the building. But infiltration is the air that we are not controlling. So that's the difference. We need ventilation. We don't want infiltration. But it always happens because buildings are not perfect, 100% perfect. So we have to reduce as much as possible the infiltration rate. What is ventilation? It's the process of supplying out the air, removing air. Okay. What is mechanical ventilation? It's the active, so that's the key word here, active process of supplying air to or removing air from an indoor space by powered equipment. Okay, so we can either supply or remove air. We need both. If we supply air and we don't remove it, we will be increasing the air volume like a balloon, and it will end up exploding. It's very unlikely that the building explodes, but if everything is well sealed and we have a constant air supply, and we don't leave that air to leave the building, well, something terrible will happen. So we have to supply and remove. We have to remove the air that is exhausted, that is, it doesn't have a good quality because there have been a lot of people breathing and perspiring in the room. So we have to remove that air, and then we need to supply fresh air. So this is the process of mechanical ventilation. With mechanical ventilation, we can control the air we remove and the air that we supply. Natural ventilation occurs as a result of only natural forces. And that's great because that means that we are not, because with mechanical ventilation, at least we need a fan, we need to move that air, and we are consuming some energy. With natural ventilation, we are not consuming energy. If we open two opposite windows, this natural ventilation will happen and we won't have any energy. And if the outdoor air is at a good temperature and relative humidity, we don't need anything else. And that would be for free. And but with the mechanical ventilation, we always have to move mechanical equipment, and that consumes energy. The good thing of mechanical ventilation is that when the outdoor air is too cold, we cannot rely on natural ventilation, because if we open the window and the outdoor air is at freezing point or below the freezing point, we lose a lot of energy, we lose a lot of heat. So mechanical ventilation is better. And then the CFM, you know that cubic feet per minute, and these are the units again, is the standard measurement for the airflow. You know, you should know what CFM is, because if you have taken systems, and I think all of you have taken systems, we have been working with the CFM, with this concept, because this is how we measure the ventilation. By the way, all these definitions are taken from the International Energy Conservation Code, this IECC. The version, the last version is 2012. These have not changed since 2012. Well, codes, I'm not stressing a lot on using codes. So there are different codes in different states. We have a different code. I'm relying on these passive house standards because they are more restrictive than the New Hampshire code. And 99% of the codes that we can find in different states, they are just copying the International Energy Conservation Code. So I think this is the source. And then, yeah, so they are adapting in New Hampshire. There are things of this international code that don't apply because the climate here is not warm and humid as in Miami. So they take this part away, and then they keep only the things that apply for this cold region. Okay, but this is the source, and I'm referring to this international source. And then we have the ventilation loads. You should remember that as well. We have sensible and latent loads. Sensible loads are related to temperature, and latent loads are related to moisture. We have this formula, and well, I have attended these teaching demonstrations from other guys, and they might use a different formula, but at the end, it depends on the units, or it depends on, but at the end, they all have the CFM. They all have a factor here, a constant, and this constant depends on the units. If you're working with international units, you will use a constant. If you're using these imperial units, you're using another one. But they all have this CFM, and this is the amount of air that we have to supply and to remove. And we have this expression for sensible, and we have this expression for the latent loads. And we have to use here the dry bulb temperature, indoor minus outdoor temperature. And here we have to use the wet bulb temperature. If you remember, when we were working with systems, we use a different thing. We use the enthalpy. Okay, so that's another way to use this. If you remember this chart. Okay, so here we can find everything. We can find the dry bulb temperature, the wet bulb temperature, and then we can find the enthalpy. Everything is connected, and we can either use the dry bulb, the wet bulb, or the enthalpy to calculate the same heating or cooling loads. Okay, but everything is related in this chart. But the formulas will change. If you use the enthalpy, we can have a different formula. Here we are using dry bulbs, and we are using wet bulb temperatures. If you use the enthalpy, the formula might change, but it's not a big issue. You need to understand that everything is related, and we can use different values or different parameters of this psychrometric chart because they are all related by this. And then the formula will change. That, well, this is the formula that we have been using for 2 years for the sensible and latent loads. I don't want to make things more complicated in this course, so we will be using the same formulas. What is this? Well, this is taken from the code, from this International Energy Conservation Code as well. And these are recommendations for ventilation for occupied spaces. Depending on what space we're working with, we will be using different CFM per person or per floor area. So we use CFM with the Imperial units. We use liters per second in international units. Okay, so here we have this. And I told you that if you remember systems, by the way, what was the CFM that we used, the value for the CFM that we used in all our mechanical systems exercises? Do you remember?
Wasn't it something like really kind of low? Was it like 3 or 5?
Nope. It wasn't that low. You don't remember? You don't remember this exercise with 20 people? What was the CFM for this? If we had 20 people, what was the CFM for this space?
Is it 20?
20, yes. 20, just, that's it, 20 or 20 times something?
Wait, no, I'm not sure actually.
Well, try make a wild guess.
I was gonna say 1 CFM per person.
1 CFM per person. No, try again. 20 is good, but try again.
Is it 20 per person?
Yes, 20 per person. So it's 20 CFM per person. And if we look at this, okay, so this is the CFM per person. In this, so it's always around 20. So here we have 20, 20, 20. If we have a smoking lounge or a public restroom, we need to increase the amount of fresh air that we are supplying. Okay, so that here we have 60 or 50, but in most of the spaces is between 15 and 20. And those are always minimum, okay? So we can always increase this value. So if we are using 20, it's good for the 15. When we have 15, we can use 20, that's fine. If we have to use 60 and we use 20, that's a big mistake. But I mean, other than operating rooms, public restrooms, and smoking lounges, if we use 20, it's fine. 20 CFM per person. Okay, so in this exercise, if we have 20 people, the total CFM is 20 times 20. And this is 400. 400. But in this, if we have 100 people, so that would be 20 CFM times 100. So that would be 2000. Okay, so this is the total CFM. It depends on the number of people. So for every single use, except smoking rooms, public restrooms, or what was the other one? Operating rooms, okay? Hospitals, yeah, hospitals are a different world. Designing hospitals, it's crazy because they have their own rules and their own codes. Okay, so we're not talking about hospitals because this is like a different, but for the rest of the, well, we have a bar, a cocktail. Yeah, when we presume that in the gambling casino, yeah, people gets excited and well, when there are a lot of people, or probably we have a gym. We don't have a gym here, but in gyms, in places in which we have a lot of people moving, sweating, especially, then we have to increase this 20. But in the rest of the rooms or the spaces, 20 is fine. Okay, so if we want to calculate the amount of CFM, and we need the CFM to calculate the ventilation loads, okay, because we have CFM here, then we need the dry bulb and the wet bulb temperature. But first, we need to calculate the CFM. So we need to know the number of people that we have in each room, and then we have to multiply this by 20, and we are pretty sure that this amount of CFM is good for the ventilation. And it can be natural or mechanical ventilation. So these 20 times the number of people, it's for both natural and mechanical ventilation. And okay, this is what we are going to calculate today. And if you want to go from, because as I told you, everything is related with this psychrometric chart. If we place here the dry bulb temperature, let's say 20, and the relative humidity, we submit. And here we have the wet bulb temperature. And we have the enthalpy. Just by typing two parameters, we can get the rest of the parameters. Equations are pretty complicated. So this is the way we can calculate the wet bulb temperature if we are working with the dry bulb temperature and the relative humidity. Okay, so we have this formula, this long formula. And well, it took me some time, but this is what I have done here in this website, in this Excel file, sorry. If you can see here, we can type the indoor dry bulb temperature and relative humidity. And here we have the wet bulb, and we have all these elements that we need, the vapor pressure, the vapor saturated pressure. Well, there are a lot of things that I figured out how to do it with these formulas. But I mean, let's check. If we have 70 and 50, so if the indoor dry bulb temperature is 70, the indoor relative humidity is 50, according to this, the wet bulb temperature is around 58. What about this? Well, first we have to adjust the settings to Imperial Units and reset. Submit. Okay, so if I'm working with 70 Fahrenheit and 50% of relative humidity, I submit. The wet bulb temperature is 58. Great. It's 58.4 and is 58.38. We're almost there. Okay. What about the outdoor temperature? If we are working with 0 Fahrenheit and a relative humidity of 20, according, let's say, imagine that it's raining and we have a high outdoor relative humidity, about 80. The wet bulb temperature is -17. With this, is more likely that we make a mistake, because when we have negative numbers, things are messed up. So we will try this, 0 and 80. So if the outdoor temperature is 0 and the relative humidity is 80, submit. And the wet bulb, it's negative 0.67, and according to this should be negative 1.6. It's not a big deal. I mean, it's not a huge mistake having this. And if we want to be on the safe side, we have made a mistake, but we have made a mistake that because if this number were higher than the number that we get from this wet bulb, I would be worried, because well, probably I'm too optimistic. But now I'm not optimistic. That's my approach to life. So that's good to me. We can use this because we are on the safe side. We are maximizing the load, so the reality will be better than my calculations, which is always a good approach to calculating these kind of things. But you see that we can't rely on one tool. We have to check different tools. Okay, so I think the indoor temperature is quite accurate, and I'm sure that if we are using other values, the accuracy will increase. So this is 32 and 80. So we use here 32, submit. So here the wet bulb is 29. And here is 28.99. So almost, yeah. So it's better. Okay. So once we have checked that we can rely on that tool, now we can calculate the ventilation loads. So as you see this Excel file, it has these features for calculating the R value, the U value, the heating loads and the cooling loads through the roof, the walls, the floors. We can calculate here the condensation risks. And here we have the windows. I will go over the windows, but I want to explain about the ventilation and infiltration. Okay, so the ventilation here. The sensible heat, these are the formulas, 1.1 times CFM times indoor minus outdoor temperature and latent heat. So the first thing we need the CFM. So here you can control the number of people and the CFM per person. This is always 20. And here we can control the number of people. You have 20 people, so that would be 400. If we have 100 people, the CFM will change. And then all these changes, all these numbers, because they are connected to these numbers here, to the total CFM, and 1.1 times this total CFM, times indoor minus outdoor temperature, and wet bulb indoor minus wet bulb outdoor temperature. So these values are taken from here, okay? So first we need to set the outdoor conditions. When we set the outdoor conditions, then we can go to these calculations. And finally, we have a heat recovery. So if you remember, the heat recovery we have heat recoveries when we are using mechanical ventilation. If we supply air and we remove the air, but we don't take this air away and we take it out of the building, but if we take it to the heat recovery, okay, so this device that we have here, I don't want to feel. Okay, so this device here is the heat recovery. Okay, it's within the air handling unit, but here we mix the fresh air, the outdoor air, with the exhaust air. And before getting rid of this exhaust air, we are taking part of the energy that this exhaust air has, because here the indoor temperature is at 70 Fahrenheit. The temperature at this point would be 70 Fahrenheit. If we have the outdoor air here, that would be 0 Fahrenheit. It's outdoors. And what is the temperature here after the heat recovery? Well, it would be something between 0 and 70. Probably would be an average. So the temperature here can be, let's say, 35 Fahrenheit. And then we need a heating coil. So we need to warm up this air from 35 to 70. Okay, if we didn't have this heat recovery, okay, so I'll do this here. If we didn't have the heat recovery, the air inside the air handling unit, or the temperature inside the air handling unit, would be 0. And then we have to go from 0 to 70. Okay, that works. This is a ventilation system. We supply fresh air at a good temperature, at a comfort temperature, and we remove the indoor air, and that's fine. But this is better because we are using the heat recovery. And then we save energy because this heating coil is working from 35 to 70. Okay, I have included this on this Excel file as a percentage, as an efficiency. And this is something that the supplier, we need to talk to the supplier. Okay, what is the efficiency of your heat recovery? 70%, 60%, 50%. Everything that is above 50, it's good. The more, the better. And I have applied this to the sensible heat. It doesn't apply, well, we have applied to both, okay. Some of the heat recoveries recover sensible heat. Some others recover also latent heat. It depends. If this heat recovery doesn't work with latent heat, then you don't have to apply this efficiency to the latent heat. So I'm assuming that we are working with the best technology and we can recover sensible and latent heat. So here, that depends on the specifications of the manufacturer of heat recoveries or air handling units. It can be 70, it can be 75, whatever. Everything above 50 is worth using. Everything below 50, it's not worth spending money on that technology because it's not efficient enough. Okay, so here we have the ventilation loads, and the total ventilation loads, it's always the heat, the sensible and latent heat. The addition, sensible heat plus latent heat. This is the ventilation load, and this is what we need. So with this file, we have the heating or cooling loads from the roof, the walls, the floors. We can calculate the ventilation load, but there's a component about infiltration load. So what is this infiltration? It's the air that enters through the windows. Well, through the windows, not through the window, through the crack of the building. So usually it's between the connection between the window frame and the wall itself, but this is infiltration. Okay, but it can come from the joints or the connection between, let's change this color. The connections between the wall and roof. If there's air leakage or the thermal insulation is not continuous or the air barrier is not something continuous, we can have these infiltration issues. And well, we need to quantify this. And how can we quantify this? It's quite difficult. And we need to test the building because in our design, there is no way to, if this is well solved, okay, we won't have infiltration here or we won't have infiltration here. But what about the real building? We need a test after construction. And this is what Peter Joost is doing as well. And this is what another field of, in the architecture is about investigating if the building is working well or not. And we have to do this by means of observation. We have to observe it. Okay, there's a mold here. There's something wrong. We have moisture, and this moisture is creating this mold. Or we can test. We can use infrared cameras. Okay, so we can take infrared pictures, and we say, oh, there's an issue here, and we don't see. It's latent. We don't see that issue until it's too late. So with infiltration, what can we use? We can use the blower door test. Okay, so this is the blower door test. Those guys are happy here. And what does it mean? Well, we are applying an extra pressure inside the room or the building. Well, usually we test rooms. We don't test the building as a whole because it's too much. We are adding a lot of pressure, and then we are measuring the rate at which this pressure is going down. And this is the rate at which we are losing air. And we lose air through the infiltration. So everything is locked. I mean, all the doors and the windows. So everything is, we don't have any opening, at least that we know of. And the rate at which we are losing this pressure is giving us the infiltration rate. We have this blower door test in our building. Well, I hope that we can use this in the near future because it's quite useful, because we have all the equipment to measure this infiltration rate. The problem is that to measure the infiltration rate, we need to create a condition in which it's very likely that we are losing air because of the infiltration. And what are these conditions? These conditions are, we have a benchmark by the ARCH360. ARCH360, I told you that is the Bible of heating and cooling and ventilation systems. So the ARCH360 recommends that the air changes per hour, the natural air changes per hour, and this is another way to measure the ventilation rate or the infiltration rate. It has to be 0.35 or less. This is according to ARCH360. According to passive house standards, this is even more restrictive, so this number is lower. But what do we have? We have the blower door test. So the blower door test, we have testing conditions, and that means that we have to create 50 pascals. So this is the pressure. I don't know if you you know what 50 pascals is. It's a high pressure. So we would feel that something is pressing, and yeah, because it's a very high pressure. So basically we're inflating a balloon. So the balloon is expanding, and the pressure inside the balloon is it's pretty high. So when we open this, the balloon that's why we have created such a high pressure. So this high pressure that we have to create with the blower door test is 50 pascals. And then at these 50 pascals, we are losing that air, and this is the infiltration rate at 50 pascals. And this is what we can measure with the blower door test. Okay. So the blower door test, this is much higher. This is less than 3, less than 5, depending on these zones. Okay, so this is the zones that we have to calculate all these kind of things. We have California and Miami and the Gulf of Mexico. This is the hot and humid zone. We have this border, Alaska. This is the zone 1. And in New Hampshire and the northeast of the United States, we are in zone 2. Okay, so we are in zone 2 when it comes to all these calculations. So we have a value when we are testing this with a blower door test at 50 pascals. So this value can be less than 3. I would use less than 3. And then we have the natural infiltration rate that has to be less than 0.3, 0.35. And how can we go from the air changes per hour at 50 pascals? So we always have this element at 50, that means 50 pascals. So how can we convert this value to the natural value? Well, we have to divide by this N coefficient. And this N coefficient comes from this table. So first we need to find out where we are. So in New Hampshire, we are in zone 2. And then what about our building? Is it well shielded? Is it normal? Or is it exposed? What does it mean? When shielded, mean that the building is not exposed to the wind. If we are in the middle of a city with high-rise buildings, the building is well shielded because we have buildings around our own building. Okay, so it's not exposed. The exposed condition would be if we have a house at the top of a hill. So this is the example of an exposed building. And then the rest is normal. Do we have a lot of trees around our building? Okay, it's not well exposed because the trees are stopping the wind. Or do we have other buildings around? Well, it depends. Anyway, well shielded, it's in the middle of in downtown. Exposed, it's at the top of a high hill with a lot of wind blowing. And the rest is normal. So if we are not working in the middle of a city, or if we are working on these conditions, I would use normal. And this N factor in zone 2 with a normal exposure is 14.8. No, sorry, this is number of stories. So this is the zone, this is the exposure, and this is the number of stories. I said 2 because a single family house, we usually have 2 above grade. We are not counting the basement. Okay, so we have 2 floors, first floor and second floor, or we have 3 floors or above. So that's it. So a single family house with 2 floors, normal exposed, zone 2. So that value would be 14.8. Okay, in this Excel file, we have here we have the value of this blower door test. It can be 2, it can be 3, it can be 5. Okay, so this is the value that comes from the blower door test. So let's say 3. And this is the N factor that comes from this table. Again, zone 2, normal, 2 floors. This can be 14.8. Okay, we can type here 14.8. We have the volume of the building. The volume of the building is the area times the height. We can change this volume, no, whatever. So here we also have infiltration rate because of the sensible heat and the latent heat. The thing is that we have to turn this in from air changes per hour to CFM. And that's a different thing that we have to understand today. Okay, so how can we convert air changes per hour into CFM? Imagine that we have this room. It's a room which is 10 by 10 by 10. Okay, and we have 1 air change per hour. That means that in 1 hour, we remove all the air that we have inside this building or this room in 1 hour. So that's what 1 air change per hour means, that we remove all this air in 1 hour. So what is the volume that we are removing? 10 by 10 by 10. So we are removing 1,000 square feet in 1 hour. So it's about volume and time. And this is what CFM is. CFM is cubic feet per minute. So it's volume, cubic feet, and time, minutes. So how many minutes do we have in 1 hour? We have 60 minutes. Okay, so to convert air changes per hour into CFM, we have to multiply by the volume of the room, and we have to divide by 60. That's it. If the volume of my room is not, let's say that this is 20 by 20 by 10. What is the volume? 20 by 20 by 10 is 4,000. Okay, so that would be 4,000. So 1 air change per hour in this volume, it's not 16.6, is 4,000 divided by 60. (4,000 divided by 60, 66.6 CFM. Okay, this is what we are doing here in this infiltration rate. So here we have the air changes per hour, we have the volume, and we calculate the CFM with this formula. Okay, so it's the volume times the air changes per hour times divided by 60. And this is the air change per hour that we have the natural one. Okay, so we start with the test, then we have the n factor, and this is the natural one. Look at this. This value is 0.2. This value is air changes at 50 pascals divided by n. It's 0.2. According to these ARCH360 recommendations, it has to be below 0.35. So it's good enough. Okay. Usually when we have this value below 3, that means that the building is tight. It's a good building. If we have this 10, that means that the building is it's quite a bad construction. So the natural value would be 0.67. So this is a bad building. So everything that is below 3, it's quite good. At this, so if we have a blower door test in our building, and the value of this blower door test is 3 or below, we can be proud of the building because it's quite good. If it's above 5, I think if we have 5 here, yep. So look at this, with 5 at 50 pascals, this is 0.3, almost 0.34. And the limit is at 0.35. Okay, so all the values that are above 5, let's say that we have 6, that would be 0.4, too much. Okay, so that measures the quality of the construction. And it has to do with the design for sure, but it also has to do with the construction company. So it doesn't depend on the architect itself. So we have to, if we design bad details, or especially if during the construction, we are not there to make sure that all the air barriers and the thermal insulation, it's a continuous line that's not broken. It's very likely that we don't have good values for the infiltration ratio. Okay, so when we are looking at this now, at these elements, so here we are comparing the thermal loads that we have because of the wall, because of the floor, because of the roof, because of the window, and the total ventilation and the total infiltration. Okay, so that's a good option because the ventilation is much more than the infiltration. Well, if we are looking at this, this is the first thing that we have to address. Okay, we have the total ventilation here. So what can I do? If we analyze this building, okay, the walls and the roofs are quite good. I have reduced the infiltration, that's good. And I have an issue with the ventilation. What can I do? I can increase the efficiency of the heat recovery. If I have a 90% efficient heat recovery, now we are reducing this. And look at the final number. So it used to be with 75, it was 30,000. If we increase the efficiency of the heat recovery, now it's only 12,000. The infiltration rate is the same. So can we do something else? Not really, because the ventilation depends on the number of people. So we cannot remove people from the building. We can't change the CFM because this is a fixed number, so we can't reduce this. The only thing we can do is to work with the heat recovery efficiency. 90, it would be almost perfect. We cannot have 100% efficiency. 70 is good enough, believe me. So if we have 70 here, probably there's nothing we can do about this ventilation load. But if we had a loose construction, it's not tight. So imagine that this value is 6 we carry out the blower door test. This value is 6. Okay, so this has increased. It was 3, and this value was 2,000 or 2,500. If it's 6, that value would be 5,000. Okay. So that's what we have to analyze now. We have to analyze the building in terms of ventilation and infiltration loads. And well, I think this tool, we can use that because by entering here the relative humidity and the dry bulb temperature and the number of people, we do have the ventilation loads. And the infiltration loads, if we are analyzing a real example and we have the results of a blower door test, we can type here those results. Let's say 3.5, 3.6 is the result of the blower door test. And then we can calculate the infiltration loads here. And then by analyzing this, we can understand, okay, is it, where is the problem? The problem is in the ventilation. When we have, if we have the right number of people and we have the right CFM, the only thing we can change is the heat recovery efficiency. It can be worse. If we didn't have a heat recovery, that would be 0, and that will rise up to 123,000. Okay. And if we are talking about large buildings, ventilation is the main issue. In single family houses, probably the roof is or the windows are the, but if we're talking about large buildings, everything depends on the ventilation. So we better have a heat recovery and we better reduce the infiltration, because then we can reduce the total amount of, the total peak load that we have here.